This seminar is being recorded. All participants who do not wish to be recorded are free to deactivate their camera, mute their microphones or leave the call. Der Vortrag wird aufgezeichnet. Teilnehmern, die mit der Aufzeichnung nicht einverstanden sind, steht es frei, die lokale Videokamera zu deaktivieren, das Mikrofon stumm zu schalten oder das Seminar zu verlassen. Alan, please.
Okay. Yes. Hi. Welcome, everyone. Good afternoon. Good morning. Yeah, I'm Alan Leneff here at R&D Materials in Exeter in the U.S. I'd like to introduce Professor Xiaohang Li. He's Associate Professor of Electrical and Computer Engineering and Applied Physics, and he's at KAUST in Saudi Arabia. It's kind of interesting how we met. We actually were looking for people in universities and other organizations to help us with some nanofabrication work that we're doing, and he had many interesting papers in this topic, and so we contacted him and talked quite a bit. Turns out maybe the specific nanofabrication issues weren't exactly what was the perfect fit, but we found out that he had many other interests in doing lots of interesting work in semiconductor lasers and LEDs, and thought he would be a great person to share his work with us. So he did his PhD at Georgia Institute of Technology here in the U.S., authored well over 160 journal papers, more than 20 patents. That's really, and he's quite young. He's won Young Investigator Awards, so he's a very prolific researcher. And I think on that, I'll let Professor Xiaohang Li take it from here.
Thank you so much, Alan. Thank you, Andres. Thank you, everybody, for inviting me to speak. I have heard about Osram when I was studying my master's degree research at Lehigh University in the US, because Osram has always been one of the top companies in solid-state lighting. And then my first project was on the development of reduced efficiency tube for green LEDs and blue LEDs. So yeah, I've always admired the work done by all the colleagues at Osram, and today is my great honor to be here to talk about our research. So the title today is boron aluminum gallium nitride, III-nitride semiconductors for optoelectronics. So first of all, I would like to have a quick introduction for KAUST, since probably most of you have not been to Saudi Arabia before. So KAUST was founded in 2009, so it's a very young university, relatively. So we are located about 1 hour north of Jeddah. So Jeddah is the second biggest city in Saudi Arabia. It is also the gateway to the two holy cities in Islam, Medina and Mecca. So we have a pretty big, international airport here, and KAUST is about 1 hour north. And we are built by the Red Sea, so we are on the west coast of Saudi Arabia, so to speak. So so although we are a very young university, but I think we have progressed very quickly in terms of research and also in terms of different ranking in the world. For example, we have been ranking #1 in the world in terms of citation per faculty. Also, we have a relatively small student population, but we have over 120 nationalities among students. So we've been ranking #1 in the so-called international diversity as well. And also there are different, other rankings you may refer to here. Also, we have a relatively balanced female to male ratio for our students. Although we are a science and technology university focusing primarily on engineering, we have 41% female student in the population. I think this is a pretty good number, relatively speaking. And in terms of solid state lighting, since all of you are doing some kind of work related to that, so KAUST is also the first campus in the world that use all LED outdoor lighting, right? So this is partially thanks to our young age, but also a very progressive in terms of utilizing highly efficient technology such as SSL. So in terms of semiconductor research at KAUST, we have about 20 faculty members and about 500 researchers, including students, postdocs, research scientists, working on different areas of semiconductors. which are listed right here. Certainly, they include LEDs, lasers, wide bandgap semiconductors. And here at KAUST, we have about 4,000 square meter of class 100 to 10,000 clean room. We can process up to 8-inch of wafer. And then we have a lot of the front end capability here for different materials, including compound semiconductor, silicon, 2D material, organics, and so on and so forth. We have some back end capability, but it's our primary focus is on front end. So talking about my lab, I've been building and leading the so-called advanced semiconductor lab. We focus on the wide bandgap, ultra wide bandgap semiconductors that include GaN, aluminum nitride, boron nitride, gallium oxide, indium oxide. But as Dr. Allen has mentioned, we have also focused on the different high index materials for the passive optics as well, such as titanium oxide. So based on all of this material, we have been working on primarily 4 areas of research. One is UV to visible optoelectronics. That is the focus today. The second one is we are also working on power and RF electronics, because the same material can also be applied for high power and RF devices. And third is we are working on utilizing some of the metal oxide for low cost and large area ICs. Number 4 is we are also working on extreme environment devices that can operate at very low temperature, close to 0 Kelvin, and also very high temperature, close to 1,000 degrees Celsius. So we collaborate, globally with many, major groups in this area. And today, I certainly hope that some of the communication and the seminar today can facilitate some of the potential collaboration with Osram in the future. So we focus on material growth to device, and then some of the IC design, fabrication, and also some primitive packaging and testing. So let's talk about the focus of the talk today, which is optoelectronics. As you know this better than me, this is the electromagnetic spectrum in the universe, right? We have very, very short wavelengths, electromagnetic waves such as cosmic rays, and also very long wavelength, wave as well. But the most important, arguably the most important spectrum to the human being, because we live most of the people live on the surface of the Earth, is the visible to plus UV and plus IR, right? So this. So this boron aluminum nitride, boron aluminum gallium indium nitride system is the perfect, is like the gift from the nature, right? That can tackle this very broad spectrum, but it's also crucial to the human being, right? So, many of you are very familiar with the indium aluminum gallium nitride system, but later I will talk a little bit about, what happened when you add boron into this family. So basically they cover a band gap anywhere from about 0.7 EV, that is indium nitride, to about 7 EV, that is boron nitride, right? So you can cover whether it's based on direct or indirect band gap, about 200 to about 2,000 nanometer, which is the most important spectrum to the human being. Yeah, so over the last 10 years or so, we have done a lot of works related to the UV to visible optoelectronics. So we have carried we focus primarily on the heteroepitaxial system by growing the materials on sapphire and silicons. We also do material science research to look at the defects and to look at doping, etc. And also we utilize different device physics to design various structures. For example, we do a lot of the polarization engineering for our devices. And finally, we focus on LEDs and lasers as well, based on the III-nitride. So as you can see, we have published quite a few papers in those areas, but because of the time limit today, I'm going to just have a few examples out of our works. So I will talk about our aluminum nitride epitaxial on silicon. Certainly, this is a very challenging topic. And then I will talk about the GaN-based and also gallium nitride-based UVC lasers. And then I will talk about our works on the gallium nitride-based micro LEDs, and also the exploration of this emergent material, which is what happened when you add boron into the GaN system. Yeah. So let's talk about the aluminum nitride heteroepitaxy on silicon 111 first. As you know, growing aluminum nitride has, you have a few options in terms of substrate selection. You can take aluminum nitride. It is ideal in terms of lattice mismatch, thermal conductivity, thermal mismatch, right? But it is very, very expensive, and there is no commercial device today utilizing the aluminum nitride substrate, right? A lot of the devices, including LEDs, the visible LEDs and UV LEDs, are made on sapphire substrate. Today is very, very cheap. You can go to 12-inch, right? Although like nobody is making LED on 12-inch, but the 12-inch sapphire substrate is available. But it has other drawback. For example, it is thermally insulating, right? And it has a certain mismatch as well. And also, it's very hard to remove aluminum nitride from the sapphire, right? You can do the laser lift off of gallium nitride from sapphire, but for aluminum nitride, it's very challenging because of the very large band gap of aluminum nitride. So, but certainly in the last 10 years, we have done a lot of work on the aluminum nitride epitaxy on sapphire too. But today, I think I'd like to focus on the aluminum nitride epitaxy on silicon, right? So in terms of silicon, silicon is to me, is the ultimate substrate if you can get high quality material on silicon because of the enormous scale of economies of the silicon CMOS industry, right? It is the dominant industry for the semiconductor area. And also you can easily remove silicon, which will be great in terms of the light extraction efficiency of a UV LED. And once you do that, you open up a lot of other opportunities such as thermal management, right? And also in the past, we have utilized this platform to make piezoelectric sensors that operate close to 1,000 degrees Celsius. That's the record for piezoelectric sensors to date. In addition, you can also make flexible, LEDs and lasers, which also open up, additional opportunities. However, it's also very, very challenging to grow aluminum nitride on silicon, right? The GaN on silicon technology has been developed for multiple decades. And today, a lot of the GaN devices, especially the power devices, is made on the silicon substrate. But the aluminum nitride growth on silicon is still at its infancy, right? So if you don't control the mismatch and the tensile strain well, you end up with a lot of cracks as shown right here. So this is from one of the sample we have grown that has a lot of cracks, right? Which will become not usable for device applications. So how do you address the strain? How do you manage the strain, right? So in the past, a lot of the study have relied on the pattern substrate. Okay, you either pattern the silicon or you grow an aluminum nitride buffer and you pattern aluminum nitride, right? So all of those technology have been effective to different degrees, but it is that the process itself is complex, it's costly. So our work primarily want to focus on how do we get crack-free, high-quality aluminum nitride on planar silicon. Okay, so how do we do it on planar silicon? So typically, as you well know, people have developed the aluminum nitride buffer to grow crack-free GaN on silicon. Why aluminum nitride? Because aluminum nitride has a smaller lattice constant, right, compared to GaN. So by having aluminum nitride as a buffer, you can provide sufficient compressive strain so that you prevent a crack formation on GaN on silicon. However, for aluminum nitride, right, if you look at this Indian aluminum gallium nitride system, I mean, there is no material with smaller lattice constant than aluminum nitride. However, because we have worked on the boron dope nitride system for a long time, we were thinking that why don't we just use boron aluminum nitride or boron gallium nitride, because those materials can create the kind of smaller lattice you need to provide compressive strain for silicon, right? That's number one. Number two is that the boron aluminum nitride tend to have more columnar growth, right? So which means that you can actually enlarge the buffer grains. That buffer grain will delay the coalescence, right? Which in turn actually also suppress or mitigate the accumulation of the tensile strain as well, right? So you kind of like one stone hit two birds, and then we can potentially realize crack-free aluminum nitride on silicon 111. So this is our epitaxial process, right? So I think a lot of you are epitaxy experts here. So you are very familiar with this. So we have three samples, okay? So the first sample, sample one, has no boron. Okay, we grow buffer layer aluminum nitride, then we grow a thicker, like about 500 nanometer of aluminum nitride at high temperature. The second sample, we have a little bit of boron, right, in terms of the boron flow rate. Here we use triethyl boron, TEB, which is commercially available as well. And then for the third sample, we have a lot of boron, right? So we compare how the boron flow or the composition of the boron in boron aluminum nitride affect the sample quality and surface roughness. So this is the in situ reflectance and also the curvature measurement. Okay, so the green one is the temperature, right? Right here, you have the reflectance, and on the right here, you have the curvature of different systems. As you know well, we can get a lot of information from those in situ data. So basically, we found that when we actually incorporate boron from the reflectance measurement, we actually delay, we can delay the full coalescence of aluminum nitride. And in addition, by having boron inside, we can also reduce the curvature, right, significantly, as you can observe here. Okay, so sample 3 with the highest flow of boron reduced the curvature by the most. However, from the left, you can see that when we have the most boron flow, the blue line, right, the surface becomes rougher and rougher, right? It's because the reflectance keep reducing here, right? So we want to see how the sample looks like in terms of from the crack perspective, but also want to look at the surface roughness, because you don't want the cracks, but also you don't want a very rough surface, which because of the heterojunction we use in the devices, you want a very smooth and nice and crack-free surface for the devices. So here are the surface of the 3 samples, 3 wafers. The first sample without boron, we have a tremendous amount of cracks that are visible to eyes. For the second and third sample, we realize crack-free surface, okay? But we noticed that for sample 3 with the highest boron flow, we get a very rough surface here, okay? So which is consistent with the in situ monitoring. And here we have the AFM study of the 3 sample at different stage of the growth, right? So for the buffer, you can see that this is aluminum nitride buffer. It has the smallest grain size. Okay, it has smallest grain size. And when you have a little bit of boron into it, you start to make the grain size bigger, reflected by the higher roughness. And then for the highest boron flow, you have the roughest surface. Okay, so this is a buffer, right? So the buffer, again, aluminum nitride, low boron, boron aluminum nitride, and high boron, boron aluminum nitride. And after you grow 200 nanometer of aluminum nitride, you can see that for the first sample, it is very smooth. The coalescence has completed. For the second sample, you start to see the coalescence almost finished, but you end up with those pits all threading dislocations. Right. For the third sample, you can see that the surface is very grainy, it's very rough. Okay, this is a very typical morphology when you have a lot of boron. And then for the final, when the whole growth finish, we end up with a smooth surface for the first sample, but also equally smooth surface for the second sample. But if you notice, we still have a lot of dislocation on the surface. For the third sample, we end up with a very rough surface with a roughness about 22 nanometer, right? So here is the X-ray characterization. We notice that for sample number 1, okay, so the 002 and 102 are all listed here. For sample number 1, we have 002 about 0.26 degree. 102 is about 0.39 degree. Those are all rocking curve. But for sample 2, we have improved quality for both 002 and 102. So actually, it's with this kind of thickness, about 500 nanometer, the quality of those samples on silicon is actually not bad. It's actually comparable, even better compared to aluminum nitride on sapphire with the same thickness. But for the last sample with very high boron concentration, we get a much larger full wave height maximum, about 0.5 degree for both 002 and 102. And here is some rough estimate of the threading dislocation, including the screw and the edge dislocation. And again, the dislocation density is about 10 to the power of 9 for the screw, and then about 10 to the power of 10 for the edge. It is still not as good compared to a thicker sapphire grown on, thicker aluminum nitride grown on sapphire. But it's quite decent if we use a similar thickness on sapphire. Yeah. So here we have the ISM data, reciprocal space mapping. As you can see here, this is the 3 samples. From here, you can see that the sample 2 has the strongest intensity, indicating the highest quality. But also based on the position of their peaks, we can estimate the remaining tensile strain. And we found that the tensile strain does decrease when you increase the boron flow, but the sample 3 has the poorest quality, right? So although it has the lowest strain, but the quality is greatly sacrificed. So here are some benchmarking data. We compare our work with the previous reports on the planar. Again, this is planar silicon 111 samples. So far we have realized the larger thickness without the cracks, and as well as the lowest full wave height maximum for 002 and 102. Of course, we are still trying to improve it so that we can push the thickness higher, which will help us reduce the amount of dislocations in the field. So next, I would like to talk about UVC lasers. This is closely related to aluminum nitride, but the works I'm going to present are primarily done on the sapphire substrate. So the UVC laser is a very important technology. In the past 10 years, DARPA has 2 research programs on the deep UV laser or UVC lasers. One is CMUVT, which I was part of at Georgia Tech. The other one is LUSTER. Okay, so both programs aim to develop solid-state compact semiconductor-based UVC lasers, and that can have a lot of applications, primarily in the detection of biochemical agents, atomic clock, Raman, and non-line of sight communication. The reason is that the commercial deep UV lasers, such as the Excimer laser here, are very, very bulky, heavy, complex, and it's not portable or mobile, right? So it's very important to develop the UVC semiconductor lasers. So to realize the UVC laser diode, you have to do 2 things. One is to achieve very nice P layers, because one of the major issue for the high aluminum diode is the hole injection, right? So you need to have a decent conductive film for the hole injection. But also you need to have a very good, the cladding layer as well as a quantum well together with waveguide as well, because then by combining with a good hole injection, you can realize the good UVC laser diode. So we primarily focus on this part, so that we want to demonstrate low threshold photopump deep UV lasers, because low threshold means that you need relatively low density of injected carriers, including holes, to realize the laser diode. So those are the works I did when I was at Georgia Tech. So at Georgia Tech, we were developing the UVC lasers on sapphire. We managed to demonstrate actually the first UVC laser below 260 nanometer. We also demonstrated the first low threshold UVC laser on sapphire as well. So and at that time, many groups were competing in this area. So a lot of the groups, such as North Carolina State, PUC, Palo Alto Research Center, also SETI and RPI, they were focusing on using the aluminum nitride substrate to realize the optically pumped UVC lasers. Some leading groups in Germany, such as FBH Berlin and TU Berlin, they are also want to demonstrate the UVC laser on sapphire substrates, and also there are some groups in China and Japan. They try to demonstrate the photopump lasers on silicon carbide and also the sapphire substrate. So our study have demonstrated the UVC laser basically from about 239 to about 266 nanometer, based on both sapphire and then also some works on the aluminum nitride substrate. We also realized quite like some of the lowest threshold, especially for sapphire substrate at that time. So in addition to demonstrating the lasers and then look at the threshold, another important property of the L-GaN-based system is the optical polarization, because depending on the relative position of the split off hole band and also the heavy hole valence band, you can have either the transverse electric or the transverse magnetic emission. Right, so when you have the recombination between conduction band and then the heavy hole valence band, you have the TE polarization. And when you have the recommendation between the conduction band minimum and then the split off band, you will end up with a transverse magnetic emission, right? So previously, people have demonstrated that the spontaneous emission, the L-GaN, will exhibit the TM and TE emission when you change the aluminum composition in L-GaN. But our work demonstrates the first TE and TM TE and TM transition for the lasers. So you can see here. So when we have lasers at different wavelengths, for the shorter wavelength laser, the TM mode will dominate. Okay, but when you move to a longer wavelength, the TE mode will start to dominate. So we see a nice transition of the TE and TM mode at about 245 nanometer or so. Okay, so this is very important for the laser diode design because this is related to how waveguide may confine the light especially for the edge emitting lasers. So after the discussion of L-GaN, so once I come to KAUST, right? So I'm very curious. Can we use gallium nitride for deep UV LEDs and lasers? So gallium nitride has a band gap about 3.4 eV, right? So if you pump it, it will emit light at about 365 nanometer, right? But how do you realize the deep UV emissions, right? So you can make it ultra thin. So because of the well-established quantum mechanics, right? When you have extreme quantum confinement, right? So you will be able to potentially generate light that is with a photon energy that is much higher compared to the intrinsic band gap of the materials, which is 3.4 electron volts. So, and in addition, having gallium nitride as a quantum well have additional two benefits. One is that you can improve the electron-hole wave function overlap because the quantum well is very thin, right? So you have a very weak quantum confined star effect. And number two is that the gallium nitride, because the most of the recommendation happen between the heavy hole band and then the conduction band minimum, you end up with the TE dominant light, right? So this is preferred actually by the UV LED because you can get a higher light extraction efficiency compared to TM polarization, and also the TE light is more focused compared to the more dispersed TM polarized light. So that is good for optical confinement as well. So and so this idea is not new. Before our work, multiple groups in Japan and the US have demonstrated the use of ultra-thin gallium nitride quantum well for deep UV LEDs, as you can see here. They can push the wavelengths down to 220 to 240 nanometer. However, there was no report of gallium nitride quantum well for deep UV lasers, right? So if we can demonstrate it, it can truly demonstrate the potential of this system for the future UVC devices. So we decided to give a try. Okay, so we grow this structure again for optical pumping on the sapphire substrate. We have a 3 micrometer aluminum nitride template with a quality right here, and then we have about 40 periods of aluminum nitride and gallium nitride quantum wells. We have a lot of periods here because we were not sure whether we can get the lasing, so we have a lot of the quantum well because we want to have a large optical confinement because the gallium nitride offer a higher index compared to aluminum nitride. And then we grow about 6 monolayers of aluminum nitride barriers and then 4 monolayers of gallium nitride quantum wells. So eventually we have a optical confinement about 35%. So here we show the X-ray reciprocal space mapping. So we realize pseudomorphic growth. There is no relaxation. And also we see some nice satellite pics here indicating the sharp interface for the quantum well. And this is an AFM image showing a roughness about 0.6 nanometer, right? So the surface is quite smooth too. So here is the high resolution TEM image. So we did realize about 4 monolayers of gallium nitride and then sandwiched by about 6 monolayer of aluminum nitride. So, and then we cleave the 2-inch wafers by lasers into different laser bars. And here we from the SEM, the clip facet is very smooth. We did not apply the dielectric dBr mirrors right here, so we have a natural facet reflectance about 0.2 for UVC wavelength. So here with the photo pumping, we demonstrated the first deep UV laser based on gallium nitride quantum wells, and at the threshold above at the pumping power above the threshold, we have a narrow line width about 0.9 nanometer, and on the right here you have the Li curve indicating the laser operation. So the threshold is about 190 kilowatt per centimeter square. So if we do a little bit benchmarking with the L-GaN lasers, which I shown earlier, so you can see that our gallium nitride quantum well UVC laser actually has a pretty decent threshold compared to the reported L-GaN quantum well UVC laser on various substrates. So this means that this material system is actually quite interesting and also maybe promising for the further development of the UVC lasers and LEDs. So in addition, I mentioned about the transverse transverse electric versus transverse magnetic polarization from gallium nitride, and this was verified by the optical pumping at below the threshold and above the threshold. So below the threshold, this is spontaneous emission. You can see that the TE dominates the spectrum because again, this is gallium nitride. If you have high aluminum L-GaN, the TM will dominate. For the above the threshold as well, we have a TE dominated spectrum, indicating that the use of gallium nitride indeed can leverage its TE dominant emission for lasers and LEDs. So next, I would like to talk about the gallium nitride micro LED, right? So we shift the wavelengths to visible, and also we look at how the scaling of micro LED and how we use different technique to optimize efficiency. So the micro LED is one of the hottest technology topics today for GaN based technologies and research. So because it can be used in high resolution display, AR, VR, it can be used for visible light communication, it can be used for smart lighting, it can also be integrated on wearable devices like smart watches. So, and recently, as you know very well, in the last couple of years, the big tech giants like Apple and Meta have launched their smart goggles, right? For Apple, it is the Vision Pro. For Meta, they have this new Orion smart glasses, right? So if you open up those systems, right, they have a lot of optic system, including waveguide, including gratings, right? But the most important probably the most important component in these smart goggles is the light sources, right, from the projectors. For Apple, it currently utilizes the micro-organic LED, and then for Meta, they use the micro-LED together with silicon carbide waveguide, right? So to further develop the efficient and compact micro-LED is crucial for the development of those VR and AR technologies in the next decade or so. So when you talk about AR and VR, right, because of the proximity to human eyes, so you need very small pixel size. So compared to iPhone 13, for example, the pixel size needs to be reduced about 10 times or so below 10 micrometer, right? But when you have a reduced dimension of the micro LED, you start to have a lower EQE, right? One of the major reasons for that is the damage. The sidewall damage during the plasma etching process. So the plasma etching process is the dominant process used to fabricate most of the LEDs, including micro LEDs. So in this process, you have to have accelerated particles from the plasma to etch and form the pixels, right? So in this process, you can introduce a lot of leakage path and the non-radiative recombination standard. And then, so this image is very nice. It illustrate that the sidewall actually have a couple of nanometer of highly amorphous layers. And those layers will trap your electrons and holes and also become the non-radiative recombination standards. So many studies before have looked at the size effect based on the plasma etching, right? So when you have a very large LED pixel, the size effect is negligible because most of your light come from area that is away from the edge. But when you move to the dimensions such as 20 and 10 micrometer in diameter, you start to notice the rapid decrease of light intensity, across the mesa, right? So it has this profound reduction of the light intensity near the edge. So how do you address it? Many groups have proposed different techniques. Some use the chemical etching to remove the amorphous layer. Some utilize the oxide passivation by ALD, and also people have utilized more, sophisticated techniques, right? Such as they want to control the current path so that the current do not flow to the sidewall, right? So and also different studies have proposed the use of etchant-free technique, right? For example, people utilize this direct bottom-up epitaxy to get micro LEDs, and then people have utilized the ion plantation, okay, to isolate the areas of micro LED. But you can still see that there are different ions inside the LED mesa as well. And also, people have tried to utilize the hydrogen plasma passivation to passivate the P-type gallium nitride, so that you can form the mesa. You can form the pixel. Yeah. So in this work, we propose the use of selective thermal oxidation process. We believe that this might be one of the more cost-effective and straightforward way compared to a lot of the techniques mentioned right here. So this is how it works, right? So we have standard epitaxial structure of micro LED with N-GaN and P-GaN on a sapphire substrate. And then, so basically the key point is that we utilize the silicon carbide protection layer on top of the mesa. And then we do annealing or do oxidation in a furnace, okay, at higher temperature. And then this silicon oxide layer will protect the layer below from the oxidation, right? And then after the oxidation, we remove the silicon oxide. So basically, the area below silicon oxide is mostly not impacted. It still maintains the P-GaN, PIN structure. But the area that is outside the silicon oxide protection layer will get oxidized by about a few hundred nanometers below the surface. Okay, so we utilize silicon oxide because silicon oxide is a very effective barrier to oxygen diffusion, right? So this has been used for silicon industry as well. So here you can see the surface morphology. So this is the surface before any treatment, right? It's just an empty wafer after the growth. So this is the area after the oxidation, but it does not have the silicon oxide protection layer. So it becomes very rough because the surface has already been oxidized into like gallium OX, right? It can be gallium O3, it can be gallium O2.5, but it's a gallium oxide complex material. So the surface that is protected by the silicon oxide during the annealing still show pretty smooth surface. So and then we utilize this to fabricate the green micro LEDs. Okay, so basically this is a preliminary demonstration of the green LEDs with different pixel size, showing our lab name, KAUST, and also the logo of KAUST. So here I show different pixel sizes from 50 to 30 to 10 micrometer. So in general, they have a relatively uniform distribution in terms of the light emission. So and then we also study the under the pseudoluminescence because under pseudoluminescence we want to examine in close proximity the light distribution across the pixel, especially near the edge, right? As you may recall, we discussed about the rapid decrease of light intensity near the edge, right? But from our study, we found that actually the light distribution across the mesa is actually relatively uniform, right? So we actually have a much reduced side effect. So here I show how the different annealing temperature affect the LED performance, because here you don't want to anneal too little, right? Because if you anneal too little, you only anneal part of the P-GaN, then you don't form a very good isolation of the pixel. But you don't want to anneal too much, because if you anneal too much, there will be some lateral diffusion of oxygen into your pixel, right? So that will affect your device performance as well. So eventually, we found that actually by comparing the wall ply efficiency, we found that the device with 4 hours of annealing shows the best device performance compared to over annealing or under annealing. And then we also look at the size dependent as well, because we want to see how the size dependent may change with the selective thermal annealing method. So here we found that we still have some size dependent effect. Okay, and then we have the on-wafer EQ decrease gradually from about 8% to about 7.8 to about 6.5%. When we change the pixel size from about 50 to 10 micrometer. However, by comparing with literatures, we notice that the size effect has been much more reduced. So that it means that this technology provides a much reduced susceptibility to size shrinking in terms of the external quantum efficiency. What is the limit of this technology in terms of pixel size? We have also worked on it's a preliminary data. We have pushed the micro LED size to about 2.3 micrometer. Okay, so vertically we anneal and oxidize about to about 400 nanometer below the surface. Okay, because we want to anneal, we want to oxidize the entire p-GaN plus quantum well plus a little bit of the n-type region, but we can change the epi structure so that we can reduce the amount of vertical oxidation. Because the vertical, when the vertical oxidation happens, you have the lateral oxidation too. That will limit our micro LED size. But so far we have pushed the size to about 2.3 micrometer, and we hope that we can push this further down to 1 micrometer or so in the future. So after discussion of the gallium nitride micro LED, I would like to talk about the exploration of the boron aluminum gallium nitride system. So I showed this graph a little bit earlier. If you look at the boron aluminum nitride and boron gallium nitride, you will find that this is a highly nonlinear alloys. Okay, not only by looking at the band gap versus the lattice constant. So, but it has some distinct characteristics. Number one, it can offer wider bandgap range to about 7.2 eV. Sorry, I forgot to mention that all of these belong to the Wu-side system, right? If you have hexagonal boron nitride, that's a different story. But we want to develop the Wu-side system because the Wu-side system can be effectively integrated into the mature Indian aluminum gallium nitride system. So for boron aluminum nitride and b-GaN, actually we like to call boron aluminum nitride BAIN. Okay, B-A-I-N. It's not I, but if you look at it as I, we call it BAIN. And for this we call it b-GaN. Okay, so let me use BAIN and b-GaN, which will save a little bit of time. So for BAIN and b-GaN, they have both direct and indirect bandgap at about 12% and 44% as the transitioning point. And also, when you add boron into aluminum nitride and gallium nitride, you can start to have lattice matching opportunities with aluminum nitride, right, between aluminum nitride and b-GaN. And also, the boron nitride and b-GaN can have lattice matching opportunity with gallium oxide and silicon carbide substrates, right? So these offer some nice opportunity in the future. And also, you have very large variation of lattice constant, right? This range is much larger compared to the range between indium nitride and aluminum nitride. So you can do a lot of strain and lattice engineering. But all in all, we can have new opportunities for both electronic and optical devices. So, but the growth is a key to realize those emerging materials, right? This is similar to the early days of indium gallium nitride when people struggle with problems such as phase separation and lattice mismatch. The same problem happened for BAIN and b-GaN, right? So before our work, the boron content of the single phase Wu-side BAIN was limited at about 1 to 2%. Okay, so for b-GaN, it is limited at about 7.4%. So we want to change that. We want to push the boron composition to higher so that we can study different properties. Okay, so without getting into too many details, but we have demonstrated the state-of-the-art BAIN by MOCVD. So we realized the boron composition from about 11%, as you can see here, to about 14%. And then the latest is about 22%, right? So, but of course, as you can see, when we have higher boron composition, the quality of the band layer start to decrease, okay? But nevertheless, now we have materials up to about 22% or so for different research for band. The aluminum nitride epitaxy on silicon earlier was actually developed based on this study as well. So this is band. How about BGAN? So for BGAN, we have developed the highest boron composition in BGAN today. It's about 15%. Okay, so and we are still trying to push the composition to higher so that we can measure and study the material science part of this immersion material. So how about the band alignment? The band alignment is very important for different devices. As you know, the conventional indium gallium aluminum nitride system has mostly type 1 heterojunctions, right? So when you have type 1 heterojunction, you always have to balance the electron blocking and then the whole injection of the EBL layer in your LED and lasers, right? But interestingly, the band and AlGaN system form the type 2 heterojunction, right? As you can see here, the conduction band edge of band 14% is about 1.1 EV higher than AlGaN, 70% AlGaN. And then the valence band max is about 0.4 EV higher than the VBM of AlGaN, right? So this is a type 2 heterojunction. So this is really interesting for the electron blocking layer because now you can block electron but allow holes to flow into your quantum wells, right? And then, but also it can be used for the barrier layer in the AlGaN-based HAMT as well. So this is maybe the first true type 2 heterojunction for III-nitrides. So this work was also picked up by Compound Semiconductors. They actually put our work as the title of the newsletter after we published this paper. So in addition to band, right, and we also look at how BGAN and also band with other boron composition have in terms of the type 2 opportunities. As you can see here, this is the DFT calculation of the band alignment for band and BGAN. When you have, this is gallium nitride and this is aluminum nitride, those two are well known, right? But when you add boron into the GaN and ARN, you start to see that the band alignment start to change pretty dramatically, across different compositions, right? This is partially reflected by from the band gap versus lattice constant, which I showed you earlier, right? So I told my student that this is actually a gold mine for III-nitride device engineering because these kind of type 2 opportunities are not possible in the conventional indium aluminum gallium nitride system. So, here's one example how we could potentially use this for the red LED, right? Many years ago, when I was a grad student, people talking about the green gap, right? Because if you want to have solid state lighting, you want to have an efficient green light. And I think Osram has done a lot of great works in that area, including LED and lasers. But also now we have the red gap, okay, or the yellow gap, red and yellow gap. This low efficiency is primarily caused by the difficult growth of high quality, strain engineered indium-rich InGaN type 1 heterojunction, right? So can we utilize the type 2 heterojunction for the red or yellow LED? The answer is possibly. Okay, so this is simulation. Okay, it's not experiment. So we basically take the BGAN layer with a composition about 12%, about 1 nanometer or so, and we put it in between a gallium nitride quantum well and sandwiched by AlGaN layer. Okay, so AlGaN here has a high composition about 60%, and we have about 2 nanometer of GaN and then 1 nanometer of BGAN, right? And because of this type 2 heterojunction, we can, although the BGAN and GaN are larger bandgap material, but because of that, we can essentially push down the optical transition energy in this quantum well to about 2 electron volt or so. Okay, so that will generate, again from the simulation, about 225 nanometer. And also this quantum well, this combination also realize the polarization matching. Okay, I will talk about polarization later, but it can also realize polarization matching. So this can also reduce or mitigate the quantum confined star effect, which is a major issue in high Indian quantum well too. So this is quite interesting, and hopefully we can do more experiment to verify this. So another interesting thing for optical devices is refractive index. Okay, so in the past, when you want to realize a good epitaxial DBR layers, you always have to balance the lattice and strain, right? Because mostly when you have a heterojunction for the DBR epitaxially, you always have some lattice mismatch. So when you want to, especially when you want to increase the delta n between the two layers, right? The higher the delta n, the better DBR, the less the number of pair you need to have. So this is a kind of a three-dimensional image that we calculated based on DFT. So here you have the lattice constant, okay? You have the boron nitride and aluminum nitride and GaN, and this is the reflective index, okay? And this is the wavelengths corresponding to the band gap, okay, of those materials. So if you look at the AlGaN layer, right? So whenever you want to have a larger delta N, you have a larger delta A as well, A being the lattice constant. But when you add boron into the game, for example, if you draw a horizontal line from left to right, you get the lattice matched heterojunction, right? Lattice matched heterojunction for the with a large delta N. Okay, for instance, like the UVA VCSEL has been very important. Actually, in the US, there have been multiple projects from DARPA for the UVA lasers, VCSELs, because it is very important for the future development of atomic clock. So, however, if you use the AlGaN GaN system, you always end up with some lattice mismatch, and the delta N is also not as large. Right here, for example, right here you have a mismatch about 0.265% in terms of lattice, and then your delta N is about 0.12. Okay, but from this graph on the left, we found that you can actually pick up about 10% boron in BGAN, and then it is entirely lattice matched with aluminum nitride. So your lattice mismatch is zero. And in the meantime, you get a large delta N, about 0.27 or so, right? So this is very promising for the future development of the epitaxial DBR for UV VCSELs. So next, I would like to talk about the polarization property of those BGAN and BANE layer. Conventionally, people have done a lot of polarization engineering for the Indian aluminum gallium nitride. So far, I have counted, there have been about 150,000 papers published with the keyword polarization for the III-nitride. Okay, so there are a lot of papers. But according to our research, okay, we have found that by adding boron into this system, we can greatly expand the spontaneous polarization as well as a piezoelectric constant, so that we can actually utilize the BGAN and BANE to create additional polarization engineering properties. And in addition, this group of material have some very interesting characteristics. For example, if you look to the right, okay, especially the blue and the purple solid and dashed line, you can notice that at a certain composition, okay, the piezoelectric constant of the purple line, sorry, maybe it's pink, okay, pink and purple, and the blue line, they will cross zero at almost the same time. Okay, this does not happen before for the other nitride materials because their piezoelectric constant will remain with either positive or negative across the composition. But this crossing at zero for BANE and BGAN is actually very, very unique. So, and our work has been also cited in the Wikipedia as well, right? So the spontaneous polarization is actually part of the pyroelectricity of the material, right? Which is common in the material with asymmetric lattice. But, I think our work was the first one that showed the pyroelectric material, such as BANE and BGAN, can have zero piezoelectric coefficient or zero piezoelectric response for strain along the C-axis at the certain composition, as I showed you earlier. Yeah, but with this additional polarization constants from Bain and Began, both spontaneous and piezoelectric, we can then play with the polarization in a very systematic way for device applications. We have built a III-nitride polarization toolbox. So in this toolbox, we don't have the conventional tools anymore, like a screwdriver or wrenches. But instead, we have different III-nitride material, including GaN, InGaN, BGaN, LGaN, Bain, and so on and so forth, and Indian aluminum nitride as well. And here we can select the right alloys or binary material for specific three-polar or nitrogen-polar devices. For example, we can pick one material to minimize or maximize the strain sensitivity for things like pyroelectricity, energy harvesting, MEMS, or we can pick up two material, nitride material, to minimize or maximize the heterointerface polarization, right? That is very important for the C-plane devices like LED laser and also transistors. Or we can pick up three material to form a double heterojunction to minimize or maximize the tunneling probability of those materials. This itself has other applications. For example, the tunneling junction LEDs. And in addition, we can pick gradient material at different range to either minimize or maximize the three-dimensional polarization carrier densities, right? So that is very important, especially for the P doping. So because of the time, I won't give a demonstration of this toolbox, but we have already used that for different things. So this is another report from compound semiconductor for one of our papers. So basically, it mentioned that the cows have predicts the polarization-free III-nitride heterojunctions on C-plane, right? So that is particularly important for LEDs. So this comes to the end of my presentation. And so today I've talked about, for our works from epitaxy to devices. For epitaxy, I focus on the aluminum nitride epitaxy on the large mismatch silicon 111 substrate. And then for the lasers, I talk about the LGaN and gallium nitride UVC laser. And sorry, I don't know why this will flip, actually. Sorry about that. So we developed both LGaN and then the gallium nitride corner well-based UVC lasers by optical pumping, and we're trying to get electrical pumping. And then I talk about the use of selective area thermal oxidation to develop etch-free gallium nitride micro LED that is much less susceptible to the size reduction effect. And last but not least, I talk about our work on the exploration of this immersion material, particularly boron aluminum nitride and BGaN. And of course, all of our works were not done by me. They were done by my graduate students and postdocs. And also, this is a view of cows at night. Of course, this is with very low exposure of camera, as you can imagine. Normally, we cannot see so many stars and the Milky Way. But this is a Red Sea. This is the symbol of cows. It's a beacon. It's a beacon of knowledge. It represents that the knowledge created cows can be utilized, hopefully, and referred to around the world. And then these are some of our restaurants and also the student apartment by the Red Sea. With that, thank you very much again, and Andreas and Alan, and for your kind invitation. I look forward to further discussion and potential collaboration in the future.
Thank you very much.